Okay, so let's start. So here is what we proved last time. We discussed homology of curves with finite coefficients, and in particular, so X was a curve, smooth, projective curve over an algebraically closed field. So what we proved is that if we are given an integer n, which is not divisible by the characteristic of the field, for example, it can be any integer if characteristic is 0, then we have and say U is open subset, so then we have the following exact sequence. We have H1 et al. Of X with coefficients in n. We have the restriction map to H1 et al. Of U. We proved that this map is injective. And then we had the residue maps to a direct sum over all I from 1 to R of Z mod n Z. And so here I have the summation map to Z mod n Z. And well, one result that we proved is that there exists an exact sequence of this form. And we also computed this group. Well, abstractly, canonically, this is big X and torsion here. And non-canonically, this is isomorphic to Z mod n Z to the power 2G, where the G is the genus. Okay, that's a sort of quick summary. In particular, this shows that these groups are finite. So which is very good to know. And also, it shows that if, say, X is if K is the field of complex numbers, then at least abstractly, this group is isomorphic to Betti homology of U with Z mod and Z coefficients, which is also a good sign that the theory is right. So, ну просто, что такое когомология открытой кривой? Ну, у вас для когомологии, классической топологии у открытой кривой тоже есть такая последовательность. Когомологии компактной кривой ограничиваются инъективно в когомологии открытой кривой, и размер у них те же самые. Эта группа, она изоморфна абстрактно. Чему, собственно? Ну вот Z по NZ в степени 2G плюс R минус 1. И хорошо известно, что для Римановой поверхности без R точек когомологии они такие же. Хорошо? Нет, хотим, например, конечности. А второе, чего мы хотим, чтобы когомологии, вообще нашей этальной когомологии, по крайней мере, с конечными коэффициентами, для многообразия над комплексными числами, восстанавливали нам когомологии Бетти. В следующий раз, то есть завтра, я докажу это в гораздо большей общности. Пока утверждение было то, что только абстрактно эта группа над полем, вот эта группа, этальная когомология, над полем комплексных чисел, изоморфна когомологиям Бетти. Да, да. Ну, это расширение Z по NZ модулей. Вот. Все здесь свободно. Very good. So notice that this condition that n is not divisible by characteristic is important. So remark is that if k is if characteristic of k is p, then and say u is not x, so there are at least one punctured point, then this first cohomology group of u with coefficients in z mod pz, we computed it using the Artin-Schreier. So I claim that this group is infinite. And the reason for this is that we have a short exact sequence of sheaves for Étale topology. Where this map takes a function f to the pth power minus f. That's called the Artin-Schreier exact sequence. And consequently, using the fact that the first Étale homology of any quasi-coherent sheaf is the same as Zariski homology of this quasi-coherent sheaf. So if u is not x, then u is affine. So this H1 Étale of u with coefficients is 0, right? And using this long exact sequence associated to this short exact sequence, you conclude that this is the co-kernel of the map from functions on u to functions on u, sending a function f to f minus f to the pth power. Okay. Right? So, for example, H1 Étale of u of A1 over Fp bar with Z mod Pz coefficients is actually an infinite dimensional vector space. So it's non-zero in particular. This is a bad sign. So this shows that homology of Étale homology of schemes in characteristic P with Z mod Pz coefficients do not behave well. Значит, как из этой последовательности следует вот это утверждение? Ну, вы просто пишете h0 от этого, h0 от этого, h0 от этого. Дальше будет стоять h1 от этого пучка, а h1 от этого равняется уже нулю. Поэтому отсюда следует, что первые когомологии — это коядро на глобальных сечениях вот этого отображения. Угу. Ну, например, если вы возьмете А1 у вас будут, что такое глобальные функции? Это все полиномы, и мы факторизуем полиномы по полиномам вида f в степени p минус f. Понятно, что это бесконечно мерное пространство получится. Вот. Да, это абсолютно формально, потому что то, что когомологии, первые когомологии с постоянными коэффициентами всегда классифицируют ZPPZ торсеры. А что такое ZPPZ торсеры? Это гомоморфизмы из фундаментальной группы в ZPPZ. Вот. Но мы знаем, что фундаментальная группа А1, она тоже очень большая. Very good. So now today I want to generalize this finiteness and something else to non-constant coefficients. I will consider cohomology of curves with non-constant coefficients. So here is a general definition. So I will define a class of sheaves that we will be mostly interested in. So these are called constructible sheaves. So first, I will give myself any schema X for a moment. So constructible sheaves are glued from what locally constant sheaves, or synonym of this is local system. So what is a local system? What is a locally constant sheaf? So F, an étale sheaf, is finite locally constant, is called finite locally constant. If there exists an étale cover, ui to x, such that the restriction of f to each member of this cover, by the restriction I mean the pullback, is constant, is isomorphic to constant sheaf associated to some, so this AI are finite abelian groups. Okay. So this terminology suggests the definition. So it's locally constant. So another way of thinking of locally constant sheaves is that so f is locally constant if f is representable by a finite étale group scheme, commutative. Group scheme. G over X. Yes. Да, это прекрасный пример локальной системы. Значит, если k алгебраически если
корни из единицы, если в глобальных функциях на x лежат все корни из единицы, то есть их ровно n штук, то тогда это постоянный пучок. Ну, потому что его, например, глобальное сечение — это что? Это множество таких, это группа таких функций глобальных, таких, что они в n-той степени равны единице. Например, если моя схема — это спектр, там, я не знаю, Q, то глобальное сечение этого пучка — это корни из единицы, которые лежат в Q. А с другой стороны, значит, если я добавлю Q все корни n-той степени из единицы, то есть в качестве U возьму просто отображение из спектра циклотомического расширения в спектр Q, то pullback уже туда, это будет постоянным пучком, z по nz. Very good. So, so if you have such a finite étale group scheme, what is a finite étale group scheme? So it's a group scheme, so that this morphism pi is a finite étale. Then I can define sheaf F by assigning to every étale open set sections of G over U. Well, let me say that this is a group of U points of G, right? These are all morphisms that make this diagram commutative by definition. So clearly, this sheaf is locally constant. Namely, we discussed this last time, that for any finite étale morphism, I can construct actually a finite étale morphism U to X such that the pullback G times U over X is a split cover. So it's isomorphic to disjoint union of copies of U. So in this case, right? So that means that for every finite étale group scheme, I can construct U such that the pullback, this group scheme, is discrete group scheme, is isomorphic to some constant discrete group A times U. And this shows that the group of sections is indeed, this sheaf of sections is indeed a locally constant sheaf. And conversely, using the faithfully flat descent, if you have a locally constant sheaf, you can construct a finite étale group scheme over X. How you do this? If the sheaf is actually constant, then there is not much to do. You can take for, if your sheaf F is this guy, then you can just take the discrete group scheme. A I times UI. And then we discussed that you can sort of glue affine schemes over a scheme X from, you can descend them. There is a kind of faithfully flat descent for affine group schemes over X. Because affine schemes over X are the same as quasi-coherent sheaves of algebras. And we have faithfully flat descent for quasi-coherent sheaves, right? So I'm saying that if you have an étale cover and you have a affine scheme over each UI, such together with isomorphisms on intersections or fiber products, then you can construct an affine group scheme over X, sorry, an affine scheme over X, whose pullback to each U is your given one. That's a corollary of faithfully flat descent.
Why so this construction will be étale?
Because when you pull it back to UI, it's going to be a split étale cover. Right, right, yeah. Okay, so another point of view on locally constant sheaves is that these are representations of the fundamental group. So if, say, X is connected, then, and say we have a point, geometric point, well, then locally constant sheaves, is the same as modules over the fundamental group. So that's equivalent to the category of finite pi1 étale x0 modules. Okay, so what is a finite étale? What this is? So I have a finite abelian group together with a homomorphism from the fundamental group to the automorphism group of this finite abelian group, right? So that's what I mean, continuous homomorphism, right? The kernel of this map is open. So why that? So I claim that, да? Очень хороший вопрос. Значит, если моя схема связана, то все слои локально постоянного пучка, они абстрактно изоморфны. Вот. И я утверждаю, что задать локально постоянный пучок — это то же самое, что задать слой этого пучка в геометрической точке плюс действие фундаментальной группы на этом слое.
Ну, еще нужно условие конечности.
Да, А конечно. That means fine. So how to see this? Well, it follows immediately from this description. Because what is a finite étale group schemes over X? So first of all, G is a finite étale morphism. So it means that the category of finite étale morphisms is the same as the category of sets with an action of the fundamental group on this set. So if I just have a scheme G with a finite étale morphism, it gives me a set A together with an action of the fundamental group. But now saying that G is a group scheme is equivalent to saying that you have a group structure on A such that this map is compatible with that group structure, right? Very good. So, for example, so how to think of this mu n in this term? So say if I have a scheme over a field K, then so mu n, I can think of mu n as a so I have the action of the Gala group of this field, right? So if I have X over, say, maybe spec K, then Gala group of K sep over K acts on mu n K sep, on the group of roots of unity in this field. So this defines a local system on spec K. And its pullback to X is what we call here mu n. Or equivalently, so if I have a map from morphism from X to spec K, it gives me a morphism on the fundamental groups, from the fundamental group of X to the fundamental group of spec K, which is a Gala group. So the representation of the fundamental group corresponding to this sheaf is obtained as follows. So you take pi 1 of X, you project it to pi 1 of K, which is a Gala group, and you act by this group on this discrete group. Very good. So now so constructible sheaves is the generalization of local systems. And so here is a definition. Okay, so I need some assumptions. So let X be a quasi-compact scheme. And quasi-separated, quasi-compact, quasi-separated. So a sheaf F is что такое квазиотделимое? Хороший вопрос. Значит, это означает, что диагональ замкнута.
Это просто.
Что? Да, что диагональ квазикомпактна, простите. Okay. So, okay, so a sheaf is constructible, finite constructible. If there exists a stratification, there exists a finite stratification, X disjoint union of Xi, where Xi are locally closed. This is, there exists a finite stratification. Such that the restriction of my F to each strata is locally constant. what is disjoint union?
Just says theoretical.
Yes, by locally closed subsets.
So if I have a line with an embedded point, then I can decompose line as line minus point and just a point, and forget about embedded point.
Yes. What do you mean embedded point?
Embedded points of importance in one point.
Yeah, so étal sheaves do not feel, étal topology does not change if you consider reduced schemes. The category of étal sheaves will not change on the reduced subscheme is the same as the category of étal sheaves on X. Okay, so no, here is an example. So let's take some finite morphism. X if map from y to x is finite, then the direct image, say, of the constant sheaf is constructed. So if y, if this map F is actually finite étal, then, so what does it mean that it's finite étal? It means that locally for étal topology, y is just direct disjoint union of copies of X. In this situation, the direct image is going to be a constant sheaf. It's just going to be the direct sum of copies of this guy. So if F is étal, then you actually get a local system. And you can even characterize this local system in terms of the representation of the fundamental group. So you have the fundamental group of Y, you have fundamental group of X. You have a map. The fundamental group of Y is a subgroup of the fundamental group of X, and you can take for any local system on Y, so representation of this fundamental group, you can take the induced representation. That will be the representation corresponding to the direct image. So if you just have a finite, any finite morphism, let's say in characteristic 0. There is some subtlety here in characteristic P. I will say a few words of this. So suppose that it's in characteristic 0. Then I can construct a stratification of X such that over each strata, this map is is étal, right? So so for example, think of map from A1 to A1 that takes X to X squared. This is an example of a finite morphism which is not étal. So over GM, this is an étal map. So if I take this constant sheaf and restrict it to GM, sorry, if I take this direct image and restrict it to GM, I just get a local system, rank 2 local system.
What do you mean that X is Noetherian?
Yeah, maybe, right, Noetherian. Thank you. So let's see, quasi-compactness, yeah, maybe, I think you're right, yes, 8 Noetherian. So, so this, and so in this example, the stratification will consist of 2 stratas, open strata and just 1 point. This is how you think of locally constant sheaves. So here is a lemma. Но она будет, значит, она будет немножко, ну, пусть поле характеристики, пусть у меня схема над полем характеристики P. Тогда, значит, что? Нет, ну, значит, характеристики 0 я доказал. Я не очень хочу доказывать это в смешанной характеристике. Ну, смешанные характеристики есть. Ну в характеристике 0 мы как говорим, что ну вот у нас есть конечный этальный морфизм. Ну, значит, по индукции. Допустим, что он сурьективен.
У нас вообще просто конечный.
Да, просто конечный морфизм. Допустим, что он по индукции. Значит, в X существует открытое подмножество, такое, что ограничение этого конечного морфизма на открытое подмножество, оно этально. Это открытое подмножество может быть нулевым, если морфизм не сурьективен. Значит, вот это будет мой открытый страт. То есть вот как я это доказываю. Значит, вот у меня есть x, y отображается в x. В характеристике 0 я бы доказал это так. Значит, я бы нашел открытое подмножество U, такое, что вот это y умножить на U над x этально. Плотное открытое подмножество. Теперь я бы обозначил буквой z дополнение. И, значит, y умножить на z над x это какой-то конечный морфизм. А теперь я бы сказал следующее, что вот это f, значит, f со звездочкой от z по nz в ограничении на u, это, это вот эта локальная система. Значит, здесь у меня есть fu, а это fz. Это f u со звездочкой. Вот. z по nz. Это локальная система. А в ограничении на z это вот это отображение. f z нижней звездочкой z по nz. Хорошо?
Сейчас, вот Z, оно просто замкнуто.
Просто замкнуто.
Почему локально замкнуто?
Оно открыто. А любое открытое множество, оно локально замкнуто по определению. Локально, ну да, ну просто что означает локально замкнутый? Что у каждой точки существует окрестность, что пересечение моего множества с этой окрестностью замкнуто в этой окрестности. Если мое множество открыто, то это тавтологически выполняется.
Тут важно сказать, что у каждой точки этого множества.
Да. Вот. Значит, таким образом, на U это локальная система, а это конструктивный пучок по предположению, по индукции. Вот. Но в характеристике P этот аргумент требует некоторые модификации. Давайте я это оставлю в качестве упражнения. Проблема какая? Что даже если отображение сурьективно, оно не обязательно, конечное отображение, оно не обязательно в общей точке этально. Это может быть несепарабельное расширение полей. Но тогда нужно отдельно рассматривать случай, тогда y можно пропустить там через Фробениус, и нужно отдельно рассматривать, что происходит, когда вы берете прямой образ при Фробениусе. Но там оказывается, что прямой образ постоянного пучка, он постоянен. это все проще. Вот надо как бы отдельно, в характеристике P надо отдельно рассмотреть случай чисто несепарабельных расширений. Okay? So that's how you, at least you prove this in the case when X is over a field of characteristics. Okay. Катя, ответ. Now, here is a easy lemma. Lemma. So constructible sheaves form an abelian category. Embedding of constructible sheaves to all sheaves is exact. So that means that if you want to compute co-kernel just in the category of constructible sheaves, is the same as computing co-kernel. Forget about constructibility, just compute the co-kernel in the category of all sheaves, and this will be the co-kernel in your subcategory of constructible sheaves. Okay, so this is I, this is, and the last assertion is that if you have any map for any map from F to F prime, if F is constructible, then so is the image of alpha. You don't need F prime to be constructible. Well, let me just, this is an easy statement. Let me explain the last point. So, well, you reduce to the following. You need to show that any quotient of constructible sheaf is again constructible. And since the restrictions, right, this functor I inverse, the restriction functor, is exact, we are reduced to showing that any quotient of a local system is again a local system. Да, да. And, well, and this should be obvious. So by locality, you reduce to showing that any quotient of a constant sheaf is again constant. But any subsheaf of a constant sheaf is itself constant. So, okay. I will not say more on this. Okay, so here is so an important example of constructible sheaves. So, okay. Let's see. Here, so ultimately, I want to prove that the category of constructible sheaves is preserved under all operations with sheaves that we had, namely the direct image and the inverse image. Well, the statement for the inverse image is trivial, but for the direct image, it really requires a lot of work. So I will, today I will kind of do an easy part of this. So let's consider another functor, extension by 0, extension of sheaves by 0.
Wait, why is this? I mean, why is the statement the direct image of constructible sheaf is constructible is not exactly this?
Well, this is a finite morphism. What is really non-trivial is that it's true for open immersions, for open embeddings. Well, say, maybe it's, yeah, so maybe it's okay. Yeah, I think for, right, you're right. So it is, even for open embeddings, you can do this straightforward, showing, yeah, you can prove that the embedding of, for open immersion, the F-low star of a constructible sheaf is constructible. So what is really non-trivial is that the same is true for the higher for the higher derived direct images. In particular, it shows, it would say that homology of a constructible, of a scheme with coefficients in a constructible sheaf is constructible, meaning that it's finite. This is really, well, we did it with some efforts for curves and for Z mod and Z, so generalization of higher dimensional varieties is highly non-trivial.
You claim that it actually holds not for finite morphisms, but
For all morphisms, right? Provided that characteristic of the base field is either 0 or it's invertible in each stock. Otherwise, it's also not true. Okay, so we will discuss this. We will prove a large part of this tomorrow. Okay, so extension by 0. So this is the following construction. So suppose, well, let J be an étal morphism. Morphism. A good example to think about is just an open embedding. So then I claim that the functor J inverse has left adjoint. Which is called the extension by 0 or J low chic. Okay? So we know that it has right adjoint, which is J low star. And now I want to construct for you a left adjoint. Okay? So how to do this? Here is a construction. Okay, so suppose I have a sheaf, F, and I want to give a construction of left adjoint. I first define a presheaf. So, and I have some W mapping to X, and I want to tell you what the sections are. And the sections are going to be direct sum over all W mapping to U over X, and here I will have simply F of W to U. Okay? That's a presheaf. And J rho star of F is defined to be the sheafification of the guy I defined over there. So, so by the way, what is J inverse of G? So let's kind of convince ourselves that this is indeed left adjoint. In order to do this, you have to recall what is J inverse. So if I have an entire open set in U, I can consider it as an entire open set on X just by composition. So this is G of U prime to X. So for rectal morphism, the direct image is something very simple. For example, if U is where just an open embedding, you would simply take the restriction. Okay? Now, I guess it's trivial that if you have a morphism of preshifts from this guy to G, then it's the same thing as given a morphism of preshifts from F to this restriction. And because morphisms to a sheaf is the same thing as morphism from sheafification, it also shows that this is joint. Okay? So think of, again, an example when this is an open embedding. Then, so what do we do here? So this section of this presheaf on W is either 0 if the image of W in X is not contained in U, and otherwise, this is just sections of F on W. So, yeah, so I write it down. So morphisms from J low star of F to any G is the same as morphisms from F to J inverse of G. Okay? So here is, again, an easy proposition, some properties of this. First of all, this functor is exact. Contrary to J low star, which is not exact. Well, so this will follow from discretion of Stokes. So let's see. So here I have geometric point. This is X. And I want to describe the Stokes of this guy. So what this is? Can you tell me what should be the answer?
It should depend on whether X is the image of U or not.
Exactly. But so here is so in the case when U is an open subset of X, the answer should be the following. So it's either the stock of f at point x if my point is in U, otherwise it's 0. Suppose that U is something like this. So I have x, and I have two-fold cover with 1 point removed. Or maybe, sorry. So this point is removed. So the fiber over this point consists of this point, say, and this point. Well, this point is removed, just consists of 1 point. So the stock of sheafification is the same as the stock of the pre-sheaf. So you just look at this formula here, and I claim that what you'll get is the following. It's going to be direct sum of stocks over all points living over my x. So this is the limit over the diagram. So I have U, I have x, I have spec k. This is my x bar, and I consider all lifts. Okay, does that make sense? Good. So in particular, it shows that this functor is exact. You need to check that it's exact on stocks. So, okay. So another property is best change. Okay. So suppose I have the following diagram. I have y mapping to x. Let's call it f. And this is u. This is my j. This is a tal. And I can form the fiber product u times y over x. And I produce some notation. So this will be f prime, and this will be j prime. And so I claim that you have the following identity of functors, isomorphism of functors. So f prime, so you start with a sheaf on x, and then what you can do? You can take, with the sheaf on y, so f is sheaf on y, and you can first take its I inverse. So go this way, and on the other hand, you can first take the direct image, and then j. Yes, so there is something wrong here. Just 1 second. That's not what I want. Sorry. I want on U, because I haven't defined this functor. Next time we will define this functor for any morphism, and then we'll have this property. But now I can't really formulate it this way. So okay, so here is what I should have said. Sorry. So I take j chic low star of f prime inverse, and right. So here I go this way and then this way, and that's the claim is that's the same as going this way. So I take J chic F inverse of F, right? Again, the previous formula would make sense provided that it had a definition of F lower chic. And that's the same formula except that I sort of rotate this. This is called the base change, and so let's prove it. So let's construct a map, morphism of functors. So how you construct it?
Проблема была в том, что у нас F, почему не могли определить нижнюю правильно? Потому что не
Ну да, потому что не детально. So let's define this. Let's construct the map. So I will construct a map from F prime inverse of F to J prime inverse F inverse of J lower chic of F. Right? So if I manage to construct this map, at least we'll get, so my goal is to produce this map first. And then to check, I need to check that this is an isomorphism. So first by adjunction, it suffices to construct this map. And in order to construct this map, I use the following. So there is a map from here, this to J inverse of J lower chic of F. Okay? Как отсюда получается вот это? Ну, давай возьмем вот эту диаграмму, вот это отображение, которое существует по сопряженности, и применим F. Да, да. Okay, so this gives me a map, and now I claim that this is an isomorphism. And in order to check that this is an isomorphism, you just use this formula. You check that it is on stocks. You know how stocks behave with respect to the inverse image and with respect to this J loss sharp. So this is isomorphism. This property, by the way, is a special case of this best change. So you take for y geometric point. Okay, so another property is that, so if J is finite et al., then J low chic is actually equal to J low star. Let's construct a map. So the construction is based on the existence of the trace map. So recall, for finite et al. Morphisms, we constructed the trace map. Right? So recall the construction. So if U is very small, then a finite étale cover, this is J. If W is very small, then U restricted to W is disjoint union of copies of W. So in this case, the group here, the sections of this sheaf on W, is just sum of several copies of sections of F on W. And this map, which we call the trace map, is the addition map. Right? So we have this trace map, and now let's use it. In particular, so what we get from this? We get a map from J low star, J inverse of J chic to of F of G to J chic of G. Да? Говорили, что любое конечное этальное накрытие тривиализуется на достаточно маленьких открытых W. Дальше мы брали сумму. Okay, so I apply this trace construction to this sheaf. This is my F. So this is still the trace map. Okay, so and here I have J low star, J low chic of G mapping to this. Because I have a map from the identity functor to this functor just by adjunction. That is a map again from identity to J low star, J inverse. So this gives me this map. Oh, sir, there is something. Yeah, that's not what I want. Let me. I think I made a mistake. I defined for you a stupid map. So how to correct it? Yeah, so да, наверное, надо вот такое отображение, смотреть отображение. Нет, а мне кажется, что сейчас у меня есть же такое отображение из тождественного функтора. Да, вот в этот. Опять же, по сопряженности у меня есть такое отображение. Вот оно мне дает вот эту стрелку. Ага. Вот, это то, что мне нужно. Утверждается, что вот это отображение является изоморфизмом. Опять же, на своях проверяете. Ну, для... Да. Okay. So the existence of the conversely, so if you have this adjunction, then the existence of the trace map follows. So if you know that J low star is left adjoint to J inverse, then you get this bijunction. Good. So what else? So here is another property. Claim so if you have a morphism J from U to X, which is étal, and étal, and quasi-compact. Then J lower chic of the constant sheaf is constructible. Okay, so let's see what do you actually have to prove here. So in this map where a finite étal map, then well, that would be even a local system. So in this case, J low chic is equal to J low star, and we already discussed that for finite étal maps, J low star of a local system is again a local system. So how do you prove that? So what do you need to check here? You need to check, so proof, well, it's not actually proof. I reduce it to not a difficult statement about étal maps. So there exists a stratification, finite stratification, such that U times xi over x to xi is finite. This is something easy to believe, and well, right? So here is a kind of an example of an étal morphism which is not finite. Take GM to GM, say x goes to x to the x squared, and remove one point from the total space. Of course, it's no longer finite, but for this stratification, you can take just the image of this point that you remove and the complement. Well, proving this amounts to the following. By induction, all you need to check is that if you have an étal morphism, then there exists an open subset of X, such that over this open subset, your étal morphism is finite. Okay? So, this amounts in the, to the following assertion, that if you have a quasi-finite morphism, then there exists an open subset, W of X, such that the number of points in each geometric fiber is the same. This is something easy to believe. So for schemes of finite type, it's really almost nonsense. For quasi-compactness, well, you need to work a little bit, not do this. OK. So once you have this statement, the result follows immediately from the base change, because the same stratification works. OK. So now, here is the result. Theorem, a promised theorem. So X is a curve over an algebraically closed field. F finite constructible. Then, and I'll assume that, well, in particular, it's a torsion sheaf, right? It's finite. So I will assume that it's skewed by some integer n, which is not divisible by the characteristic. All right? So if characteristic is so for some n not divisible by characteristic. If characteristic is 0, then this condition is empty. Then the claim is that homology of x with coefficients in f, all finite, and HQ is 0 for q greater than 2. In fact, if x is affine, then HQ is 0 for q greater than 1. That is a stronger assertion. Okay? So again, this condition is important because, as we already observed, for x equal a1 and f equal to z mod pz, this group is infinite. So I don't have much time left, and on the other hand, I don't. I want to. Well, let me explain a key step. So proof. Well, first you do some kind of déversage. So so you can take f, you can find open subsets such that this is a local system. And then J lower chic. So U is an X. Lower chic of this guy, by junction, it maps to F. Well, this is an embedding. And in this exact sequence, F prime has finite support. So that means that if you, well, this sequence shows that if you know the result for this sheaf, and you know it for sheaves supported at finitely many points, which reduces to basically to nothing, right? This is homology of spectrum of algebraically closed field, because our curve is algebraically closed field. You know the result for f. So it suffices to prove the result for extension by zero of local systems. Да, для кривой. Да. Okay, so, and here is the, now I will explain the key step. Okay, so key step. So you need a little bit more work to show that, to reduce it to the case when x is smooth. Well, otherwise you pass to normalization, and again you use that the result is true for sheaf supported at finitely many points. So x is smooth, and f is of the following form. So you have open U in X, and this is J, and F is J lower chic of a local system. And this is local system. Local system moreover, by again using some diversage, you can assume that this is a local system of Z mod LZ modules, where L is not divisible by characteristic of K, and this is prime. L is prime. This part of the argument is similar to what we did once for Galois homology, right? So any local system is skewed by integer n, then you can write n as product of powers of primes, and then using induction, you can actually assume that this is a vector space over FL. So this is really what we need, and here the argument uses again this trace trick, method of trace. So pick a finite Galois cover U tilde over U, and this is H, such that H upper star of L is constant. Well, is isomorphic to FL to some power. Right? I can do this. Everything, yeah. So I have a Galois group of this cover, which is G. And again, as we did for Galois homology, I take the Silov subgroup of G. So I factorize this. So this is what will be the factorization. This has prime to L cover, and this is L primary cover. Okay, and this is F. So this corresponds to, again, a Silov subgroup, H, G, Silov L subgroup. And then, so you use, you take, so you have U, you have U prime, and then, so this is F, and this F sits inside smooth projective curve X, smooth curve X, and let's take the normalization of X in U prime. That will be my X prime, and the map is F prime. That's non-normalization. This is also a smooth curve. And And here I have J. And this is J prime. Okay? So, and then what you do, you look at H1, HQ et al. Of X with coefficients in J lower chic of L. That's what we are interested in. And I claim that this group embeds into HQ et al. Of, sorry, I need more. So HQ X with J or chic of L, and I want to embed it to HQ of X prime with coefficients in the pullback F upper star F inverse L, and here I have J prime. Okay? So first I claim that there exists an embedding like this. And how does it follow? Well, it follows from the existence of the trace map. So you have HQ of X J lower star F lower star F inverse of L. Right? So there is this trace map. And this group is isomorphic to HQ et al. Of X with coefficients in F prime low star F J prime chic F inverse of L. Okay? So why is isomorphic? Because just by, this is a morphine, so homology of X prime with coefficients in any sheaf is equal to homology of X with coefficients in this. And using the fact that, okay, and now I claim that these two guys are equal. And this is the best change property. The two sheaves are equal. Okay? So what we get is, so we have this map. This is the pullback map. And we have the map in the inverse direction. This is the trace map. And the composition is multiplication by the degree of this map F. So trace composed with, well, the composition of this map and the trace is multiplication by the degree, which is co-prime to L. This means that this is injective. And finally, F inverse of L has, so this is a local system, and it has a filtration with GER isomorphic, associated graded isomorphic to Z mod LZ with constant shifts. Why that? Because this corresponds to a representation of the fundamental group. Since the pullback of my local system to U tilde is trivial, this representation factors through H, where H is a C of L subgroup. So I have again a representation of a L group on some vector space over FL. And every such representation admits a filtration whose successive quotients are trivial representations, right? First of all, you have invariant vectors, then you can take the quotient, you apply this procedure again. So this guy admits is an iterated extension of constant shifts. So for constant shifts, you know finiteness and you know the vanishing, right? We proved it for mu L, but remember that there is no difference between mu L and Z mod LZ, provided that you work over an algebraically closed field. And therefore, this group is finite, and you know the vanishing. Okay, I'll stop here. So this is how, using the trace, you reduce very general method that allows you to reduce statements with non-constant coefficients to statements with constant coefficients. We will use it many times later. Да. А L любое число простое. Взаимно простое с характеристикой. Да. Да. Ну, если оно L квадрат кручения, ну, вы напишите L как расширение двух локальных систем, которые L кручения.